We've discussed three different mechanisms which remove amplitude from the propagating seismic wavefront. And these different mechanisms were the transmission loss. We had this product of 1 minus reflection coefficient squared terms all the way down to some reflector from an nth interface. And we had the spherical divergence loss, which we showed was proportional to 1 over the wavefront of the radius wavefront or the distance traveled. And then we also had amplitude loss through absorption. It's a conversion of mechanical energy into heat energy. And we could characterize that as a function of R or T. We could also do that here for spherical divergence loss, but we explicitly noted the dependence here for the amplitude loss associated with absorption. We also emphasized or made a point that the two-way transmission loss is an energy loss, not an amplitude. It's proportional to amplitude squared. And we said that we were going to come back and talk about that in a little bit more detail, so we'll do that now. Specifically, if we look at the energy loss associated with two-way transmission of the wavefront down and back up through a sequence of layers with varying reflectivity, that the energy is proportional to the product of these terms. The amplitude is proportional to the square root of this product of terms times the reflection coefficient from the nth interface. So amplitude is shown over here, basically square root of this series of products. And you can see that it's considerably less than the energy loss. So it's less by the square root. Over here we have about 12%, and I guess on this scale it's just about half. So we drop from about 12% energy loss to an equivalent 6% or so reduction in amplitude. But an important distinction, because the actual amplitude loss, and you as an interpreter, if you're an interpreter or as a processor, you're interested in restoring the amplitudes of a seismic display so that as best you can, the amplitudes in the seismic section correspond to or are proportional to the reflection coefficients that are encountered in the subsurface. So this is the distinction between the amplitude and the energy in the two-way transmission loss that we talked about, and we're specifically looking at amplitude losses associated with spherical divergence and attenuation. Now here all I've done is we have a fairly complicated stratigraphic section here, and we indicated that one could take a fairly rigorous approach and actually use density and sonic logs and actually calculate foot by foot what the energy or the amplitude loss would be based on those reflection coefficients as you went from point A to point B in the subsurface. Or we could do something like this and look at, on average, the amplitude loss for in this case, a sequence of 100-meter thick layers with reflection coefficients that alternate sign from 0 to 6,000 meters. So every 100 meters we have a reflection coefficient, and it goes back and forth either by an amount 0.02, plus or minus 0.02, or plus or minus 0.05. So just think of this as a sequence of layers. We've got 10 layers, let's say from 0 to 1,000 feet, 60 from 0 to 6,000 meters. Meters. And so that we can see that we have about a 7% decay in amplitude for an average reflection coefficient of 0.05, but only a 1% drop in amplitude for an average reflection coefficient of 0.02. In the example that we showed here, the average reflection coefficient was about 0.02, but we had some rather large reflection coefficients in there. So on average, that loss is around 1% over this 6,000 meters. For the larger average reflection coefficient, about 7%. So now if we come to absorption and we look at the amplitudes associated with absorption loss, we see that for a really small alpha, 0.0001 inverse meters, that the amplitude loss is on the order of about 40%, 45% or so from a source amplitude of 1. If we increase that absorption coefficient to 0.0005, then we can see a much more significant amplitude loss. We're just graphing this equation here. And then for alpha 0.005 inverse meters, we can see that we have a very rapid loss of amplitude in the propagating seismic disturbance. Now the decibel scale is often used because, well, one thing, for these exponential functions, that turns them from a kind of an exponential plot into a linear plot. And we can see here, the much greater separation between the absorption losses with an absorption coefficient of 0.0005, for example, compared to that of 0.005 inverse meters on this decibel log scale. So, and the dB scale is just 20 times the log of some reference amplitude over the amplitude. So this could be your source amplitude over A of R. So here we have spherical divergence, and you can see a very rapid decay here, a very rapid drop. By the time we get to 100 meters here, we've lost 99% of the amplitude in the signal, and then we just continue to drop even further. So we're down to, at about 500 meters, we're down to 2,000ths of the amplitude of the source. And by the time we get to 1,000 meters, we're down to about 1,000th of the amplitude of the source amplitude. And this is the spherical divergence amplitude drop shown on the decibel scale. So nonlinear. We see more character as we go from 100 meters to 6,000 meters. It's kind of the extreme drop that we see here is not so extreme here. We would be able to see more of the character of the variations as we go from 1,000 meters out to 6,000 meters, for example. Now when we combine these losses, we're multiplying transmission. The transmission amplitude loss times the absorption loss times the spherical divergence loss. And this would be the combined losses over here. And you can see the combined losses are, again, very extreme. We get down to about 1,000th of the source amplitude here at around 700 meters. And in the first 100 meters, the wavefront amplitude drops to only 1% of its source amplitude. Now on the decibel scale, this drop again is stretched out and over this interval. So we drop at 100 meters to about 40 decibels. And then out at 6,000 meters, we drop to 100 decibels below source amplitude. So this graph attempts to represent the processor's challenge. We have the loss mechanisms combined here. We have the transmission amplitude decay, amplitude loss. We have the attenuation loss, e to the minus alpha r. And then we have the spherical divergence loss, r. Now, the processor, in some way, is going to have to come up with a reciprocal of these terms. The processor wants to remove these terms. So the function that they have to develop is the reciprocal of this function, so that we have the transmission amplitude drop in the denominator. We have r in the numerator. And instead of e to the minus alpha r, we have e to the alpha r. The inverse of the absorption loss in the numerator. So this would be the reciprocal, this would be the correcting function. If we multiply this times this, we get basically a 0. So we have eliminated the losses in that way by taking the inverse of this loss, of these different loss terms. And that's really the challenge for the processor, because we want the amplitude of a reflection event, we want the amplitude of the reflection to be proportional to R. This is our goal. So in a true amplitude seismic processing sequence, the processor goes through this process of designing a function which would be the reciprocal of the different loss terms: the transmission amplitude decay, the attenuation decay, the spherical divergence loss, all of which are portrayed here. Tries to design some kind of a true amplitude recovery function which will eliminate this term and just give us A0 R sub n, so that we have the amplitude of a reflection at a distance R being proportional to the reflection coefficient. So this is the processing objective: to get amplitudes which are proportional to reflection coefficient. So as a challenge for you for the next time, consider this problem. Take a look at it at a distance of 100 meters from the source. The amplitude of a P wave is given as 0.1 millimeters. And at a distance of 150 meters, the amplitude diminishes to 0.0665 millimeters. What is the absorption coefficient of the rock through which the wave is traveling? And this is a problem that comes from a good text, Robinson and Crew's text, goes back to 1988. And don't complicate things, we're only dealing with absorption here. But take a look at this before next time, see what you can come up with for the absorption coefficient. And as a challenge, you might also consider what the source amplitude was in that particular case. But we'll come back and talk about that next time. Thanks for joining us, and see you next time.